So, the last class we introduced the fact that with Lewis theory and also with the molecular geometries and electron geometries, we can get an idea of how the shape of the molecules are, and we also can predict the sort of bonds that we have there. However, there is a next level on what we can do talking about bonding in molecules. And that's the model that we call the valence bond theory, right? This valence bond theory allows us to describe as the bonds as the electrons are in valence orbitals. And when making a bond, we have one electron on each of the valence orbitals on each one of the elements involved in these bonds, right? So, these orbitals that are involved from each one of the atoms in bonding can be of two types. Sometimes we can have the pure atomic orbitals, the one that we have been usually talking about, the S, the P, and the D orbitals. Or we can also use a new set of orbitals that are called hybrid orbitals. These hybrid orbitals are coming from the fact that we can mix atomic orbitals to get a new set of orbitals. It's a theoretical model, right? It's a theoretical model. It's a sort of the atom using the basic atomic orbitals to build a new set that are better to build bonds. And also, it's a model that we use in order to be able to describe or to agree with the electron geometries that we might have in the different systems, right? The key part in this is that the overlapping of these orbitals, either hybrid or pure atomic orbitals, is what gives origin to the bonds. And when you have two of these hybrid or atomic orbitals interacting, this overlapping of the orbitals is what is creating the bond. And the electrons there in that overlapping are going to have pair spins, right? Probably remember that when we built on the Lewis model of bonding, we say that, for instance, for those dashes that we use representing bonds, those are representing the fact that we had two electrons there, and those are pair electrons, pair in terms of the spin, right? So we can do a note here that electrons in bonding pairs are pair, right? In terms of the spins, one spin up and one spin down. That's what we meant by pair spins, all right? Well, one more of the reasons why we, as chemists, we decide to build on this model of hybrid orbitals is because we need that new set of orbitals many times in order to agree with the electron geometries that we have on different molecules. And there is something that I want to say right now, and is the fact that when you want to get into the hybridization scheme for different atoms, what you should be looking at is the number of electron groups around a central atom. In other words, what you should be looking at is to the electron geometry. You have this table, right, with the electron and molecular geometries on one side, and the other side you had the electron geometries, right? You had the electron geometries there. So, what we want to do is to go to this table, and let's check that right now, because that will allow us to talk about these hybridization schemes. So, as you can see here, what matters for the hybridization scheme is the number of electron groups. When we have two electron groups, we say that the hybridization scheme will be sp orbitals. We'll get into explaining what that means, right? The corresponding electron geometry when you have two electron groups is linear. Right? The next number of possible electron groups, 3 electron groups around a central atom, right? Maybe that's something that you can take note there. This is the number of electron groups around a central atom. If we had 3, the corresponding electron geometry is trigonal planar, and we call that hybridization scheme sp2. sp2. And this is how those orbitals are going to be distributed, right? They are going to have the same geometry as the trigonal planar geometry, right? Well, the same for the linear geometry. The two hybrid orbitals are going to be like this, yeah? They are going to be making an angle of 180 degrees. When you have the trigonal planar electron geometry, the angle between those hybrid orbitals that we call sp2 is 120 degrees. You can move to the next level. 4 electron groups around the central atom. The corresponding electron geometry is tetrahedral. The corresponding hybridization scheme is sp3, right? And in this case, we had 4 of those. 4 hybrid orbitals. 4 hybrid orbitals, right? When you have sp3 hybridization, when you have sp2 hybridization, you had 3. When you had sp hybridization, you had 2. And there are more possible combinations of atomic orbitals in order to get different hybridization schemes, right? We are going to be mainly working with these 3, sp, sp2, and sp3, all right? So I'm going to move here again to the presentation. So why it is important to use these hybridization schemes? Well, let's think about one example. The methane molecule, CH4. When you had CH4, well, we say that we had carbon at the center, we had 4 single covalent bonds with the hydrogen atoms, right? The corresponding electron geometry is tetrahedral. Again, what we care about for hybridization schemes is the electron geometry, or the number of electron groups around a central atom. But in this case, since we had 0 lone pairs and 4 bonding pairs, or 4 bonding groups better, right? That corresponds also to have a molecular geometry tetrahedral. We know from this concept of the electron geometries that the angle here is 109.5 degrees, right? Let's think about that versus the orbitals that carbon has available for making bonds. You remind the balance electron configuration for carbon. It ends on something like this: 2s2 with 2 electrons, and then the set of 2 p orbitals, 3 of them, each one or 2 of them with 1 electron. That's the balanced electron configuration for carbon. Now, if you think about these orbitals, the representation of these orbitals is something like this. Let's say that this we have y, x, and let's say that this is c, the 3 axes, right? The x orbital is something like this. The s orbital is something like this. It's a sort of symmetric sphere around the origin, having electron density, right? And this set of p orbitals will be something like this. One in the y-axis, right? Another one in the z-axis, right? And a third one around the x-axis, right? These are the 3, or this is a representation of the 3 p orbitals that we might have there. The symmetry of those is like building around the 3 axes, So if you think about this, the angles here between these orbitals are 90 degrees between any of those 2, right? The angle between, let's say, the y and x p orbitals is going to be 90 degrees, and it's the same for the 3 of them. That angle is not going to account for this angle that we have on the actual representation, also on what has been measured for methane, for instance. So this basic model of the pure atomic orbitals won't allow us to explain what the electron geometry for methane is tetrahedral. So we need to build something better in order to try to explain that electron geometry, right? The bond angles observed experimentally show that the valence bond theory must include a hybridization component in order to be an accurate model for bonding. That means to have a new set of orbitals created from mixing pure atomic orbitals, right? The reason for that is because the pure atomic orbitals, the given electron density geometry, cannot explain the electron and molecular geometries. So we need to build a better model for that, right? So what would be that better model? That better model are the so-called hybrid orbitals. Hybrid orbitals. Some things to say about the hybrid orbitals. First of all, they do not exist in an isolated atom, right? They only form when atoms come together to bond, right? It's a theoretical tool, sort of, right? These hybrid orbitals are going to have different shapes and orientations than the corresponding pure atomic orbitals, right? When we talk here about atomic orbitals, we are talking about the pure ones, And these hybrid orbitals are generated by combinations of pure atomic orbitals. In that sense, whatever number of orbitals you get at the end should be equal to the number of atomic orbitals that you use on the mixing, right? On the mixing. The hybrid orbitals of an atom are equivalent in shape and energy. These two things are extremely important. They are going to be completely equivalent in shape, and they are going to have the same energy. They are degenerate. And these hybrid orbitals are also going to have less energy than the orbitals that are not participating on mixing. Those orbitals not participating on mixing are going to be called anhybridized orbitals, right? Just to show one example, let's say that we get one s orbital, right? Just one of those, and we mix that with one p orbital, right? One p orbital. Let's say that we do the mix of that. The corresponding set of hybrid orbitals that we are going to get are something like this. They are going to have the same shape, right? One is going to have a sort of high electron density to the left. The other one is going to have a sort of high electron density to the right. But they are completely equivalent in terms of energy and also the shape. Right? So we say here that we had created two hybrid orbitals. And since we mix one s and one p orbital, we call this sp. Ideally, we are going to put an exponent corresponding to whatever number of those orbitals we use on the mixing. Since here we are using just one, well, we don't put a number one here, right? We just call that sp orbitals. Or hybrid orbitals, to be more precise, right? This is like mixing two different regions of electron density to get two new but equivalent regions of electron density. Right. This is one example. We are going to look into this sp hybridization in detail, but I want to talk about the three ones that we have, or at least three of the ones that you have on that handout. The sp3, the sp2, and the sp hybridization. So let's start with the sp3 hybridization. This hybridization scheme will appear when you have a tetrahedral electron geometry. Remember, what we care about is the number of electron groups around a central atom, so the electron geometry. Any central atom surrounded by 4 electron groups has a set of 4 sp3 hybrid orbitals, right? For hybridization, what matters is the number of electron groups around the central atom, or in other words, the electron geometry. The sp3 orbitals appear when you mix one valence s orbital with three valence p orbitals to yield four equivalent sp3 hybrid orbitals. So let's use again these CH4 molecules as an example. If you do the Lewis model for this, and let's enhance that model with including the molecular geometry, it will be something like this. Carbon here, hydrogen here, another hydrogen atom here, and one more right here, right? It will be something like that. You can see here that around the central atom there are four electron groups around the carbon atom, right? That means that since we had four electron groups around that carbon atom, the corresponding hybrid orbitals are going to be sp3 hybrid orbitals, right? Zero lone pairs, all those four electron groups are bonding groups, right? The electron geometry here, is tetrahedral. So these three things are going to be sort of equivalent when talking about hybridization. Four electron groups, electron geometry tetrahedral, that means sp3 orbitals, right? We need to have four sp3 orbitals because we had four bonds in this case. Right? So in terms of the atomic orbitals, what is happening is something like that. These will be the valence orbitals, these ones here at the bottom. This will be like the corresponding valence electron configuration or valence electrons orbitals for the carbon atom. We had the 2s and we had the 2p orbitals. It's like taking all these four orbitals, right, 1s and 3p orbitals, and mix them to get the corresponding four sp3 orbitals. Now the electrons also matter. Let's see, we have 1, 2, 3, and 4 electrons here. We had 4 electrons in total in the valence shell for the carbon atom. And with the hybridization scheme, we built 4 equivalent in energy sp3 orbitals. So those 4 electrons are going to go on each one of these sp3 orbitals, right? And it's like getting those electrons ready to make bonds. These 4 sp3 orbitals are completely equivalent. They are completely equivalent in the sense that they're going to have the same energy, the same shape, right? The same energy and the same shape. And they are like this. You have the drawing there. It's a better drawing what you have there. But those 4 are something like this. And each one of these are around the carbon atom, having 1 electron ready to make bonds. 1 electron ready to make bonds. Right? So, this is a representation of what's going on there with this mixing. Right? 1s orbital and 3p orbitals, the px, py, and pc orbitals. Right? To get the 4 sp3 orbitals. Here you have the corresponding geometries or electron densities, right? This is at the end the electron density of the hybrid orbitals. Note that it has a tetrahedral geometry, right? That tetrahedral geometry is in agreement with the fact that when you have something like CH4, the electron geometry is tetrahedral. It's tetrahedral, right? So we can think about the bonding now using these hybrid orbitals. On the CH4 molecule, well, we had carbon with this set of sp3 orbitals, 4 of them, each one with 1 electron. And then we also have the hydrogen atom. Well, the hydrogen atom is going to have only 1 electron. Just for the purpose of making the pairing of electrons, let's put this spin down for the hydrogen atom, right? Because for all the other electrons on the hybrid orbitals, we had the spin up, right? So the bonding, again, using these sp3 orbitals will be something like this. The sp3 orbitals surround the carbon atom, 4 of them, right? Each one of these is going to have a corresponding electron with the spin up, and then the 4 hydrogen atoms will be around here. Let's say that this is the first hydrogen atom. It's going to have 1 spin down. That will be pairing with that one on the sp3 orbital. The same will be happening here. The hydrogen atom, 1 spin down. An hydrogen atom here, 1 spin down, and 1 hydrogen atom here with the spin down, right? That overlapping, here we have sp3 overlapping with the 1s orbital on the hydrogen atom, right? This is the corresponding bond now. That is the corresponding description that we can use for that single covalent bond now. A single covalent bond between carbon and hydrogen happens because we have the overlapping of sp3 orbitals with 1s orbital on the hydrogen atom, right? Right. Let's talk a little bit more about sp3 hybridization. So it happens that every time that carbon is making 4 single covalent bonds, right, you will be having sp3 hybridization. And let's consider this molecule, ethane, C2H6, right? Well, the Lewis model for this will be something like, maybe we have the carbon atom here, the other carbon atom here, and then each one of these will be completing the 4 bonds with hydrogen atoms. Something like that, right? The electron geometry around each one of these carbon atoms is still being tetrahedral, right? The electron geometry for this of one of these carbon atoms is a tetrahedral electron geometry. So that means that each one of these carbon atoms are going to be sp3 hybridization. It's going to have sp3 hybridized orbitals, right? The carbon-carbon bond is made by the overlapping of 2 sp3 orbitals. So here what we have is, for instance, for this single covalent bond, is the sp3 overlapping, right? And for the bonding with the hydrogen atoms, what we have is the 1s orbital from the hydrogen atoms, right? This is another hydrogen atom, 1s orbital, then the hydrogen atom, right? Here in this overlapping, we'll be having the 2 electrons, the 2 corresponding electrons. All these regions where the orbitals are overlapping are going to have the 2 electrons, or the highest probability of having the 2 electrons, right? Remember that orbitals are nothing else but electron density, So the sp3 overlapping, or the overlapping of sp3 orbitals, is what gives origin to this carbon-carbon bond. It's a single covalent bond. It's a single covalent bond in this case, right? Well, I want to write something here. For common atoms, the sp3 hybridization will appear when we have, for instance, carbon making 4 bonds, right? Or when we have oxygen making the 2 single covalent bonds with the 2 lone pairs, right? Or when we have nitrogen making 3 bonds with 1 lone pair. for oxygen and nitrogen, since they have lone pairs, these lone pairs will be located on one of those sp3 orbitals, right? So oxygen atom will be using two sp3 orbitals to put those two lone pairs. The nitrogen atom will be using one sp3 orbital to put that lone pair. And the other three on the nitrogen atom, the other three sp3 orbitals will be used for bonding, right? Now let's build on the other kind of hybridization that we might have, sp2, right? Now this sp2 hybridization will be happen when we have a trigonal planar electron geometry. Again, every time you have a trigonal planar electron geometry around a central atom, that corresponds to that atom having the sp2 hybridization, right? Any central atom surrounded by 3 electron groups has a set of 3 sp2 orbitals, right? The reason why it's 3 is because you are mixing one of these, one s, and 2 p orbitals. So 2 plus 1 is 3. That's the reason why you get 3 hybrid orbitals. 3 hybrid orbitals. One valence orbital mixes with 2 valence p orbitals to yield 3 equivalent, right, sp2 orbitals. 3 equivalent sp2 orbitals, right? One example of when that hybridization scheme is going to happen. When you have the molecule H2CO, we have been putting this molecule in many different ways with the formula. I also written something like CH2O, maybe another way. But this is equivalent. In terms of the Lewis structure, is like having the carbon atom here at the center, a double bond with the oxygen atom. That oxygen atom will be having 2 lone pairs. And then we have here the hydrogen atoms making single covalent bonds with the carbon atom, right? In this case, you can think about carbon to be the central atom. Carbon is the central atom. And you can see that around that central atom we have 3 electron groups. 3 electron groups. 3 electron groups, again, is equivalent to have sp2 hybridization. Hybridization, right? Is the same, or this is also equivalent to have the trigonal planar electron geometry. Trigonal planar electron geometry. So these 3 things are sort of equivalent. 3 electron groups around a central atom, sp2 hybridization, trigonal planar electron geometry, right? So how that happens? Again, we can use the standard atomic orbitals. Let's say this will be on the carbon atom. And again, we are referring here to the valence orbitals. The valence orbitals. Now we are going to get one of these, or the only s orbital available, and instead of taking the 3 p orbitals, we are going to take only 2. Only 2. This guy here that is out of the hybridization scheme is going to be called an hybridized p orbital. An hybridized p orbital. It is not participating on the hybridization, right? The unhybridized p orbital. So we are going to get, since we are mixing 1 here from S and 2 from P, we'll get 3 sp2 orbitals. Well, 3 sp2 hybrid orbitals. Again, note here that they have the same energy. The same energy. Since these orbitals will be in agreement with the electron geometry, the corresponding representation of this will be, in this case for carbon, like carbon having those 3 sp2 orbitals, right? Making this angle of 120 degrees. 120 degrees. Each one of these is representing 1 sp2 orbitals. It's having the trigonal planar geometry. Please note that the sp2 orbitals the hybrid orbitals are lower in energy than the unhybridized p orbital. That's always going to happen. Every time you have unhybridized orbitals, those are going to be higher in energy than the hybridized orbitals, right? So doing this mixing of this hybridization is also going to lower the energy of the orbitals. So that's also sort of convenient for many molecules for stability, right? Or at least to put those electrons available to make bonds, right? Again, 1s orbital. In this case, mixing the two p orbitals will be the px and the py orbital. You get 3 equivalent sp2 hybrid orbitals, which will be having the trigonal planar geometry. Trigonal planar geometry, right? Now, what's going to happen with a hybridized orbital? Well, when you have sp2 hybridization, you might think about the following. In this case, we have been talking about carbon. It's like having the carbon atom here, and then the sp2 hybrid orbitals will be in the same plane. Say something like this, right? The three of them are in the same plane. That's the reason why we call that geometry trigonal planar, right? So this is an sp2, sp2, and sp2, right? And if that were carbon having the sp2 hybridization, each one of these orbitals is going to have one electron. But then there are one unhybridized orbital. That unhybridized orbital will be here, above and below the plane. This red thing is representing the p orbital. In this case, it will be the pc orbital. The pc orbital, right? This is the corresponding unhybridized p orbital. And that orbital is also going to have one electron available for making bonds. Going to have one electron also. So in total, in that case, the carbon atom is still having 4 electrons available to make bonds, just that they are configured in a different way than, let's say, the sp3 hybridization scheme, right? So again, going back to this molecule, H2CO, we know, we recognize that there is a double bond between the carbon and the oxygen atom, all right? So we will be seeing something like this. The carbon atom will be having the 3 sp2 orbitals, something like this, right? Well, the oxygen atom, if you think about the oxygen atom, around the oxygen atom we also have 3 electron groups. That also corresponds to the oxygen atom having 3 sp2 orbitals and 1 unhybridized p orbital, right? So the oxygen atom is also having this, the 3 sp2 orbitals, and then each one of these, the carbon and the oxygen atom, is going to have 1 unhybridized orbital, something like this. I'm going to try to exaggerate this thing because I want to show the fact that these orbitals, the unhybridized orbitals, they are overlapping. They will be having some sort of overlap, right? It's not as strong as the overlap that you will be having when you have orbitals touching end to end, right? This is called an side-to-side interaction. It's not as strong as the end-to-end interaction or overlapping of orbitals, right? But this overlapping here of the p orbitals is also going to create a bond, right? It's going to create a bond. So let's put labels here. This is sp2, sp2, sp2 here. For the oxygen atom, we have sp2, sp2, and this is sp2 also, right? Those 3 orbitals in the plane are sp2 hybrid orbitals. And this one is a p orbital, a hybridized orbital. And this one of the carbon atom is also a p, a hybridized orbital, right? So what is happening, for instance, on the carbon atom? Well, we learned this. From the hybridization, we'll be having 3 equivalent sp2 orbitals, each one with 1 electron. And then there will be 1p unhybridized orbital with 1 electron. On the oxygen atom, we'll be having the same kind of hybridization, but we are going to have more electrons on the orbitals. Why? Well, for oxygen, you had 6 valence electrons. 6 valence electrons. So, from the 3 sp2 orbitals, 2 of those are going to be holding the lone pair, and just 1 will be available for making bonds. The other one, the p orbital, the unhybridized p orbital on the oxygen atom, will be also available to make bonds. Right? And the hydrogen atoms will be just having the 1s orbital. So the hydrogen atoms will be something like here, right? With the 1s orbital, 2 electrons on each one of these overlappings. This is the hydrogen, the s orbital, right? That will be that for the carbon atom. And then each one of these overlappings are going to have 2 electrons, right? And also here, 2 electrons. And on the sp2 orbitals of the carbon, of the oxygen atom, we'll be having 2 electrons also. 2 electrons also, right? Here we can say that the carbon double bond with oxygen is because we have sp2, and pp overlaps, right? We have the overlapping of those set of orbitals in order to get the corresponding double bond. Let's see where else this sp2 hybridization will apply. When you have, for instance, the BH3 molecule, in that case, the electron geometry around the central atom is trigonal planar. Well, for boron, we only have 3 valence electrons. When you do the hybridization, you will be mixing, let's say, this set of orbitals, the 2s and the 2 of the 2p orbitals, right? You do the hybridization, these 3 electrons will be located here to make bonds. And the unhybridized orbital, in this case for boron, will be empty, right? We only need 3 electrons to make bonds. So the 3 sp2 orbitals will be used for that. And then here, having the sp2 orbitals, the boron atom will be making the overlapping with the corresponding 1s orbital on the hydrogen atom. This is the hydrogen atom and the 1s orbital. Each one of these overlapping regions, again, will be having 2 electrons. Right? So, the boron-hydrogen bond corresponds to be sp2s, or 1s better, overlapping, right? In other common atoms, you will be seeing the sp2 hybridization. For carbon, will be happening every time carbon have a double bond with whatever other element, right? Every time carbon is having a double bond, it will be sp2 hybridization. The same for oxygen. Every time oxygen is making a double bond with the 2 lone pairs, that will be sp2 hybridization. And for nitrogen, can also make a double bond. We'll be having 1 extra bond and then the lone pair. So for those 3 common atoms, you will be having sp2 hybridization for these cases. All right. Let's look at one more. The sp hybridization. the sp hybridization. This sp hybridization will be happening every time we have a linear electron geometry. A linear electron geometry. Right? Any central atom surrounded by two electron groups has a set of two sp hybrid orbitals. In that case, it's the mixing of one valence s orbital with one valence p orbital to yield two equivalent sp orbitals, sp hybrid orbitals. One example of when that's going to happen, the C2H2 molecule. To make sense of this in terms of the Lewis structure, we need to have the carbon atom at the center, or one of the carbon atoms, making a triple bond with the other carbon atom. And the fourth bond will be completing by making single covalent bonds with the hydrogen atoms. Right? You can see here for any of these two carbon atoms, we have an electron geometry that is linear. It's linear. Or in other words, you say that you have two electron groups around each one of these carbon atoms. Right? That is always going to be equivalent to say that we have sp hybridization. Hybridization. Right? We have a triple bond there between the carbon atoms. In terms of the atomic orbitals, the balanced ones, for the carbon atom, is like taking the 2s and use one of the p orbitals, right? We are taking these two. We mix them to get two sp hybrid orbitals on the carbon atom, right? These two guys that are out of the hybridization, they are going to be called again unhybridized p orbitals. But now we have two of them, two unhybridized p orbitals, right? Two unhybridized p orbitals. Those unhybridized p orbitals are going to keep the same geometry as the pure atomic orbitals. Well, there are actually pure atomic orbitals still being the same, having the same electron density as before mixing, because they are not participating on the mixing, right? Again, please note that these ones are higher in energy than the hybrid orbitals. These are higher in energy. The unhybridized orbitals are always going to be higher in energy than the hybrid orbitals. So let's see. When you mix one s and one p orbital, in this case we are using the px orbital, you can get two sp hybrid orbitals, right? These correspond to the electron density of sp hybrid orbitals, right? Two electron density regions, right? 1 and 2. Two electron density regions, right? So let's see again for this example that we know that has a triple bond between the carbon atoms and single covalent bonds between the carbon and the hydrogen atoms. The hydrogen atom again will be using just the 1s orbital with one electron, but the carbon atoms will be using these sp orbitals and the unhybridized p orbitals. Two of them. Again, we have 1, 2, 3, and 4 electrons. Those 4 electrons will go like this. 2 of them on the sp orbitals, and the other one on the p orbitals, on the unhybridized p orbitals. All right? So let's see the following. Let's try to represent this molecule again with the corresponding overlapping of orbitals. I'm going to try to draw here a plane again. We'll be putting here a carbon atom and carbon atom. If you check, the sp orbitals are going to have a linear geometry. So here, I'm going to move this a little bit to the right. It's carbon atom. something like this overlapping. Then the other sp orbital will be right here, right? Those orbitals are on the same plane, and actually they are also in the same line, right? All these orbitals are in the same line, This is sp, 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 and sp, hybrid orbitals, right? Now what's going to happen with the unhybridized orbitals? We'll be having one here above and below the plane for each one of the carbon atoms. In some way, these orbitals handle to interact or to overlap side to side, right? And then we also have the other unhybridized p orbital, right? Let's call this the c-axis, and let's call this the y-axis. So we have unhybridized orbitals on the c and the y-axis, right? For the two of them, right? This carbon is also having this py orbital. It's getting kind of weird now to represent this stuff, right? I don't know. Let me use a different color maybe for this one here, right? Represent that this will be overlapping with this color, and then maybe these ones here in green are overlapping with these ones in green here, right? There will be one more here for this unhybridized orbital, something like this, right? And those are also interacting. Right? Those are also interacting. So we have two interactions side to side from the unhybridized p orbitals. You can find in the textbook better representations of this kind of drawing, right? But it should be true here that on this triple bond between carbon and carbon atoms, what we have is one overlapping of sp orbitals and two overlaps of unhybridized p orbitals, right? So in this case, we can say that the triple bond between carbon atoms is due to the following overlaps: sp2, sp2, and then let's say py, py, and pc, pc, right? Overlappings. Right? We have three regions where orbitals are overlapping. And that's the reason why we had a triple bond. Right? Well, the other sp orbital on these carbon atoms will be used to make the corresponding bond with the hydrogen atom, right? Each one of these interaction or overlapping regions is going to have two electrons, right? I'm not going to put those electrons there because the plotting is already pretty crowded. But each one of these is going to have two electrons, right? Two electrons, one here, another one here, and so on, right? So this is the sp hybridization. Another example, when you have this molecule, for instance, BCl2, beryllium is going to have two valence electrons. Those two valence electrons will be located on corresponding sp orbitals, ready to make bonds, right? If we have beryllium here at the center, since the electron geometry here is linear, right? Remember here the electron geometry is linear, or two electron groups. That means that we have sp hybridization. Beryllium will be at the center, right? sp orbitals here for the beryllium atom, two of those that will be used to make bonds with the chlorine atoms, right? Well, the chlorine atom is actually going to have sp3 hybridization. The chlorine atom is going to have sp3 hybridization. It will be using one of those sp3 orbitals to make this overlapping and then the corresponding bond, right? So that would be another example. 2 electron groups around the beryllium atom also creates what we call sp orbitals. For these common atoms, the sp hybridization corresponds when you have the carbon atom making a triple bond, right? Here, one of these will be sp2, and the other one will be p, or hybridized orbitals. The oxygen atom cannot make 3 bonds, but nitrogen atom can make a triple bond, right? So for nitrogen, it will be something like this. And then the lone pair, This lone pair for the nitrogen atom, when having sp hybridization, will be located on one of those sp hybrid orbitals, right? This one will be p and hybridized orbitals to make the double and then the triple bond, right? Or the second and the third bond with a corresponding atom. Right, let's think about these different molecules and check what will be the corresponding hybridization on each one of the atoms. This representation of different molecules lack the corresponding lone pairs on oxygen and nitrogen atoms. So there are 3 different analgesics. Let's try to identify the hybridization on the indicated atoms. Again, for many of them, we are not having the lone pairs. Well, for aspirin, we are talking about only carbon. From now on, the only thing that you probably will need to remind yourself what is the corresponding hybridization is to count the number of electron groups around. For this carbon atom, let's say we have 1. Remember that no matter if you have double or triple bonds, that counts only as 1 electron group. So we have 1, 2, and 3 electron groups, right? 3 electron groups. The electron geometry is trigonal planar, so the corresponding hybridization should be sp2. The same or something similar happens for this carbon. 1, 2, and 3 electron groups. 3 electron groups around. Again, the electron geometry is trigonal planar. So the corresponding hybridization should be sp2. Tylenol, acetaminophen, right? Please be aware that this oxygen atom is not having the 2 lone pairs. Please put those lone pairs there. This nitrogen atom is not having the lone pair. Put the lone pair there. Let's check what else. I think of all the ones that we are being asking for, those are the only 2 that we need to put the lone pairs. But for all these molecules, they are not putting the lone pairs here. So those oxygen and nitrogen atoms will be having correspondingly 2 and 1 lone pairs, right? So let's check for this oxygen atom. This oxygen atom right here. You can see there that the lone pairs are going to count. And this oxygen is making a single covalent bond with the hydrogen atom. You will start seeing in organic chemistry that they don't like to represent that bond. They just put OH, but OH means that you have a single covalent bond between oxygen and hydrogen. So in total here, we have 4 electron groups. 4 electron groups. The corresponding electron geometry is tetrahedral. It's tetrahedral. So that means that the hybridization is going to be sp3, right? Please work all the other examples or all the other atoms there. We can check that in the next class. I hope you have a happy break, happy Thanksgiving for all of you, happy holidays. I will see you on Monday.